It's a great pleasure to have Sadi Ramírez Solano today speaking at our CosKASI ECR seminar. He's a PhD student under supervision of Mariana Vargas at UNAM. And he's going to tell us about redshift space distortion in the era of DESI.
Okay, thank you for the invitation. Yeah, of course, I'm going to talk a little bit about the redshift space distortion and how the surveys are constraining some parameters that we want to know in cosmology. And first of all, dark energy is a mysterious and poorly understood component of modern cosmology. It is needed in order to reproduce the accelerated expansion of the universe, comprising around 70% of the universe composition. And its existence is inferred from observations and remains enigmatic, with no known particle or field to explain its nature. So understanding dark energy is crucial for comprehending the structure of the universe. The Dark Energy Spectroscopy Instrument, or DESI, is a fourth-generation experiment that will lower uncertainties 1 order of magnitude compared with the previous generation. DESI will provide us with a more accurate three-dimensional map of galaxies and quasars that we have had. The DESI survey is currently being carried out using the Mayal 4-meter telescope situated in Arizona, in the desert of Sonora, in the United States. The surveys include a focal plane that uses 5,000 fiber positioning robots, in addition to a set of advanced spectrographs that obtain data through the fibers. The main goal of DESI is understand the nature of dark energy. And it uses as a key observables the BO and the RSD. It uses the tracers that are the luminous red galaxies, the emission line galaxies, quasar, and liminal alpha forest quasars, working in a redshift range that goes from 0.4 to 3.5. DESI will work with 4 tracers, and in this plot we can see that the previous generations, like the Scar Digital Survey or EBOS, had a small amount number of galaxies. For example, for the ELGs, we are going from 2,000 numbers of galaxies to 18 millions. And even the redshift range is increased by 0.5. The other tracers, we have something similar. Maybe we have we don't have this big comparison with the data, but we are also increasing the numbers for all the tracers. By the first time, we have the QSO. DESI will explore the area in the sky around 15 square degrees, 15,000 square degrees. This is more or less 33% of the total area of the sky, and this will be achieved in 5 passes of the experiment. Here I show you a calendar which basically says that by the end of the 2023, we will finally the DESI year 1 data And this is important because we need to, by this time, to have the tools to be able to extract the cosmological information from this data. So as a key observable, DESI will be working with these two, the PAO and the RSD. The first one is the baryonic acoustic oscillation, and these are fluctuation in the density of the baryonic matter of the universe caused by acoustic density waves in the primordial plasma, while the redshift space distortion are an effect due to the peculiar velocities of galaxies that make the spatial distribution of galaxies to be distorted. I will focus in the last one, in the RSD. So when we use the data from an experiment like DESI, we are provided with the angular position and the redshift of the objects, the galaxies, or the tracers. So in order to convert this redshift into distance, we need to use the equation 1, where we have to specify the current values of the composition of the universe, the amount of dark energy, the matter and radiation, and the curvature as well. However, when we observe these objects, the redshift that we measure is distorted due to the peculiar velocities of the galaxies because of the gravitational interaction between among these objects. And what we observe is that the redshift observed will be equal to the sum of two contributions. One due to the expansion of the universe, and the second one due to gravitational effects. And consequently, if instead of working with the redshift, we can convert this into distance using the equation of the slide before. So we can rewrite this as 4. So the position that we observe, that we will be, I will be calling this the redshift position, will be equal to the real position multiplied by 1 plus the effect of the peculiar velocities. So this shift leads to redshift distortion in galaxy clustering in redshift space. So, for example, we have one effect called the Gaussian effect. So if we have, for example, an spherical overdensity, and we set the observer below the overdensity, for example, here where my mouse is, when we observe the farthest point of this overdensity, this point, we will have two contributions. So one due to the expansion of the universe and another due to the gravitational interaction that in this case, as a matter of example, is going towards to the center. So when we sum these two contributions, it will make that the point appears to be closer to us. In the other case, when we focus on the closer point, the peculiar velocity will make it to appear more far because the velocity goes towards the center, but this is more far from us. So at the end, this is going to give us a result. That is that the overdensity will be squashed along the line of sight, as I put in this image. There is another effect that is called the fingers of God. And it is given at small scale in such a way that the parallel component of the peculiar velocity becomes more important compared with the flux with the Hubble flux or the expansion of the universe, and we observe an elongated overdensity. That is this one. So when people saw this like the first time in the data, they saw these patterns, but and they looked like fingers, so they call it fingers of God. So in order to study these effects, we use the two-point correlation function, and this function gives us the probability given a random position of a galaxy, give us the probability to find another galaxy given the distance. That is the equation 5. In the case of statistical homogeneity and isotropy, it only depends of the magnitude of the separation, but because of the distortion of the redshift space, we don't have this case. It is very useful also to define the power spectrum, which is defined at 7. That is just the Fourier transform of the correlation function. So how this helps us to understand more about the dark energy and the gravity models? Well, the study of the RSD allows to get constraints in the F sigma I parameter. And this allows to discard different gravity models. In this plot, we can see two different models, the lambda CDM and the DGP. And we can see how they fit the data from surveys like EVOS and BOS. Here, well, the lambda CDM is the solid line and the dashed line is the DGP. So we here I also plot the expected data for DESI, and it covers a big range in the redshift. So in this way, we can discard different models, just watching what model fits better the data. And in this case, we can see that the lambda CDM model best fits the data. The theory that we use in this analysis, particularly the analysis that I'm doing, is based in the Lagrangian perturbation theory. In this frame, the position, the Eulerian position of the fluid elements in the universe is written in terms of the Lagrangian position plus the Lagrange displacement field phi, where at the very beginning, if we set the initial, both quantities must be equal, the Lagrangian position and the Eulerian position. So conservation of matter against the coordinate transformation give us the equation number 9. That this is that we have the same amount of matter in the Lagrangian space and in the Eulerian space. This equation can be written in terms of 10, where we are using the overdensity. So assuming that at a very early times, the overdensity in Q will be much lower than 1, and we can have this expression and get 11. That is the overdensity expressed in terms of the Jacobian. In the question 12, I just write the definition of the Jacobian. And if I replace this equation in 11, I get the next equation where I can set the different orders for phi in such a way that the two linear order, what we have are these two expressions. The last one is in Fourier space. And these are the equation for the Seldovich approximation. Since phi is longitudinal, we can invert this like 13 using the growing solution for the overdensity, the D plus. And this equation is expanded in this way, and it is solved iteratively. So in order to get the second order, we need the first order and so on. The Lagrangian displacement to order n is given by 15. And as I said, we first solve the equation for the first order, and then the second order, and the third order. And in the next, I am only going to use these three orders. And adding the cold dark matter density field, and using, for this case, the conservation of matter, we can obtain the equation 17, which is this equation, just multiplying by this delta and integrating over the space. And we get this expression. So the real space density field is given by 18. Using the definition of the correlation function, applying to the cold dark matter, we get 19. And after some manipulation, we obtain the cold dark matter LPT correlation function, where here in the delta refers to the difference between the Lagrangian displacement. So in convolution, that is the way how we get these terms, and LPT, the Lagrangian perturbation theory. So the CLPT, we expand in anterior series the nonlinear pieces out of the exponential. So we get 22. This is the correlation function for CLPT to one loop. So this function, what gives us is the correlation function, but it is evaluated in the real space. And when we get the data, what we get is data in the redshift space. So we need to go for this space to the redshift space. And the way that here I'm following is using the streaming model. The streaming model describes how the fractional excess of pairs in the redshift space is modified with respect to its real space counterpart. So when we have this probability function, we can pass from real space to redshift space. And what we need to know is the form of the pairwise velocity distribution function. This is this one. And well, the next step is using a Gaussian solution. I mean, the Gaussian streaming model. So again, working with the conservation of the number of objects, we can obtain 24. And the correlation function in the redshift space will be given by this expression where the m needs to be this expression. We are redefining the expression here, so there's nothing more. And here, the important thing is expand the generating function m into cumulants. And well, first taking the logarithm and then expanding in cumulants. And the solution for the cumulants are given by the equation 28. And if we replace this expression into the 26, I think, 26. Yes. We get 29. And evaluating the generator function j equal to k, we get the next expression, and we only focus on the second order. The next cumulants we ignore them, and only taking the cumulant to second order where they have the next solutions. The first order is the correlation function in the real space. The second order is the velocity distribution function, and the second order is the pairwise velocity distribution function. And yeah, this is all that we need in order to be able, once we evaluate the expression with only the second order terms, it allows to get an expression that can be solved analytically with respect to k. And finally, we reach to the equation number 33. This equation gives us the correlation function evaluated in the redshift space, and it needs the correlation function evaluated in the real space, in addition to the velocity distribution function and the pairwise velocity distribution function. And of course, the Gaussian streaming model is something like it doesn't need CLPT. We can use another model in order to get these three quantities, but here in this analysis, I'm gonna use in this way. We also incorporate the EFT terms into this theory of CLPT plus Gaussian streaming model. And we use a code written in C that computes the correlation function using the theory of Zvonimir Bla, Emmanuel Pastorin, and Martin White, following this paper. And they add effective field theory parameters. Well, the structure is determined by the symmetries of the theory, and it allows to improve the precision of the correlation function. Here, for example, I put the correlation function that is obtained from the Lagrangian part from LPT. And here, well, this is the integral of this quantity that is defined here. Is the equation that I showed before. But these two first lines are the standard theory, while the other three terms are the new terms due to the EFT theory, where here we have the bias, the Lagrangian bias terms, and the EFT parameter alpha. So, well, in order to extract cosmological information from surveys, we need to use a theory that is the theory that I showed in this slide. So we need to use a cosmology of reference in order to get a power spectrum template that is the input for the theory for CLPT. Once we have the outputs of CLPT, we can use them to get the correlation function in the redshift space using Gaussian streaming model. But here we need to assume fiducial cosmology, where we use some values of these cosmological parameters. And in the case that we are not using the true value, we will have something wrong. So in order to quantify this error, we introduce the Alko-Paczynski parameters. So our modeling use all these steps, and it allows to get a chi-square once we have the simulation or the data, a covariance matrix, and with these elements we can explore the parameter space via MCMC and get constraints for the parameters that are free in our theory, like the F, the V1, V2, the bias parameters, the sigma effective, and the EFT parameter and the bias, in addition to the alphas parameters from the Alko-Paczynski effect. This Alko-Paczynski effect refers to a geometric distortion when we are using the wrong cosmology. And as I said, for example, if we have an overdensity, an spherical overdensity, when we use the wrong cosmology in order to convert the redshift into distance, what we will have is something more squashed, like an ellipse. So this deformation, well, we get this deformation along the line of sight and perpendicular to the line of sight. And this deformation is quantified by these expressions, 34 and 35. These expressions are equivalent to the 36 and 37. These two expressions are easier to have implemented in the pipeline that I'm using for extracting cosmological information. So in DESI, we have something called the DESI mock challenge, and this project has as an objective to build different analysis pipelines to extract cosmological information using different theories. So here I had a contribution using my pipeline, working with the theory that I mentioned. So the objectives in mock challenge were implementation and validation of the different models. In the case of CLPT plus Gaussian semi model, demonstrate a consistent behavior for the DESI year 1 precision that we expect to have this data by the end of the year. Check consistency of the results with something called the fixed amplitude simulation and the standard covariance matrix, and compare precision between the different templates and the different theories. So in this mock challenge, we used the unit n-body cosmological simulation for testing all the models. And here I show some specification of the simulation, like the particle mass resolution, the redshift of the catalog is very closer to 1. The covariance matrix that was used for this mock challenge that was created using 1000 of mock for the multiple of the correlation function in a cubic box of the gigaparsecs. So here I show some results of this mock challenge. And we can see how different groups get the accuracy and precision for the simulations. We can know that more or less all the models are within 2 sigmas from the true value of the cosmology. Okay, an alternative approach is called the full cosmology fit. So in the standard analysis, the cosmology of reference is fixed in each iteration. In this approach, what we have is that in each iteration, we are varying the input of the linear power spectrum. I mean, we don't have the cosmology of reference. It, of course, requires more time to evaluate all the parameters. So we need to work in the code in order to accelerate the calculations. But at the end, we are varying also the parameters from the linear power spectrum, but we can get constrained for the cosmological parameters instead of the F and the alphas. So, okay. In this alternative approach, for example, we are having better constraints for the results. Here I show you a triangular plot for the cosmological parameters using a full cosmology fit for the mean of the N-series mock, using the CLPT plus Gaussian semi-model plus the EFT parameters. And we have our parameters in good agreement. For scales are up to 30, we have all the parameters below 1 sigma. And in the case of S min equal to 26, we get the parameter below 2 sigmas. Another alternative approach is called the shape fit. And this concept incorporates one additional term, one extra effective parameter. And it says that with this parameter, we can capture the same amount of information as the full modeling approach, having the advantage of being more faster than the other one because this uses a fiducial cosmology. And it don't need to calculate the linear power spectrum when we go for each iteration. So this was proposed in Britt et al. In this archive, and they use this relation to get the new power spectrum where they add this new extra parameter that change the slope of the power spectrum. So we introduced this formalism of shape-fit in configuration space. This shape-fit method was tested in Fourier space, but in configuration space, its performance has not been tested yet. So here in the configuration space, what we have to do is to get the linear power spectrum in order to use the CLPT theory and get the correlation function. And with this correlation function, using the equation of shape-fit, we can omit some calculations and get the new correlation function evaluated in the shape-fit power spectrum. So we add the Alko-Paczynski parameters, and finally we get the correlation function. In the KP5 project, we want to evaluate the different compressions against the full modeling in order to see that they're obtaining the same amount of information. And we are comparing using some simulation given by DESI to test this comparison. Here I show you a triangular plot where we add this formalism to get the constraints for the CMAS data from the data release 12. And yeah, we are in this step of comparing the results against the full modeling approach. Well, we are also comparing the Fourier space versus configuration space. So, for example, in this plot, we can see that well, we have two codes. One is the EFT GSM, that is the code in which I am working, and the other one is the FOLPS. This other code works in Fourier space, and we are testing their performance in these two different spaces. Here in the left, we have the plot comparing the best fit for the full shape. We can see that these two models compares in a similar way. In fact, we get better results for omega CDM, and in AS, I think false get better constraint, but the two models are very close to the true values, around below 1 sigma. Here we compare using the shape-fit methodology. We have a similar behavior for all the parameters. Maybe the exception is the alpha perpendicular, where the EFT GSM is more far from the true value. So, well, accelerating calculation with new tools has become important in this new era of vast data volumes. So neural networks have emerged as a powerful tool for accelerating all this complex calculation and doing the analysis much more faster. Here we are implementing the neural network in order to train the neural network with the monopoles, quadrupoles, and the hexadecapoles of the theory of CLPT plus Gaussian streaming model, adding these effective field theory parameters. This plot shows how we are getting these errors compared with the true values, the correct values of the multiples, and we are getting errors below the 1%. So in this approach, to ensure a well-sampled distribution, we use the Korobov distribution. This distribution allows to sample all the space in a very good way. So in our approach, we need to calculate over this space 50,000 of multiples, and we use another 5,000 multiple for the validation set, and we reserve another 5,000 for the assessing performance during the test and get the statistic that I showed before. We follow the methodology of Joseph De Rose, Shifan Chi, Martin White, Nicholas Cochran, that comes in this archive. And we tested this with the N-series MOX. The N-series MOX catalogs are 84 individual catalogs. They are in a cubic box of 2.5 gigaparsec per site. They have the following cosmological parameters. And the results that we are obtaining for this simulation are here in this triangular plot, where the dashed line is the expected value. We can see that all the parameters are almost in the peak of the Gaussian, with the exception of the AS, but pretty close to the true value. And yes, we are getting very good results using the neural network, and using this methodology allows to get faster analysis instead of waiting more or less half of a second for getting the correlation function. We are waiting 60 times the time minus the time of that. So the new data sets require greater precision and efficiency. So it is important to develop methodologies like the neural network or new technique compression that allows to get robust conclusion in less time and be able to do the analysis for the big amount of data that the DESI will provide us. So here I show you the working group of students that were working with Mariana Vargas, Alejandro, who is working the KP4 project, Jenny Meneses, she's a master student. She's working in the KP5. This is me. Hernan Noriega, working in the KP5 project. working with neutrinos also as well, working doing his PhD. Brenda Isamar, she's working in their master's degree. She's in his first year. Well, I think this is time. Thanks a lot.
Thank you for this great presentation. So you ended up really well in time, so that leaves us a good amount of questions. So Faye, do you want to go first?
Okay, thanks for the talk. Can you go back to the Gaussian stream model slide?
Sure.
Yeah, no, the next. And the next, the expression of I think the next slide.
This is the next slide.
And the next, sorry, the
This?
next. Yeah. So I remember there are two free parameters in this M0, the f prime and f prime prime. So I didn't see that parameter in this equation. So how do you deal with that parameter?
So did you mean how we add these parameters in?
No, is this B1 the Bayesian galaxy Bayesian parameter, right?
Yeah.
So what is B2 here?
Here is B2.
Yeah.
Well, B2 appears in this expression many times. But no, I didn't get the question.
Okay, so which code you have used to compute this M0?
So the code that we are using?
The code.
Yeah, it is called the Gaussian tuning model EFT. I can give you the path of the where you can find this code. We have this code. We have all these parameters implemented in that code. So that's the question where you can find it.
Yes.
I can after the question I can add the path to the code here in the chat.
Okay.
Let me look for this path.
Yes. And yeah, I'm confused how you figure out the value of B2. I remember this B2 is a free parameter. You may need to fit.
It's a free parameter.
Okay.
Other questions? Rodrigo?
Hi, thanks for the talk. Can you go back to the slide where you compare full shape analysis with shape fit? The constraints you get from the MCMC. Yeah, that one. Yeah, that one. So is there an intuitive way of understanding why there is such a large bias in F sigma 8 in the shape fit approach?
Yeah, I'm not sure because the shape fit approach changes the slope of the power spectrum. I couldn't say a right answer to this right now.
So in a few words, what are the difference between FOLPS and your AEFT GSM model? So what changes? Why does the bias go in different directions? Is it easy to understand or?
maybe, well, I'm not sure because I think I need to have a better understanding of Phelps. But well, first of all, we are working with different scales, and there is no correlation between the scales in there's not something that is equivalent to the scales of Fourier space and the configuration space. So we can expect to have the same behavior for both.
Easy, thanks.
The Forbes works in Fourier space, and you're working in redshift
configuration space, right?
So trying to compare the two scales. So you are at larger scales than Forbes, is that right?
Yes, yes.
Okay. So Forbes should be less sensitive to M, because you see this disagreement F sigma 8, but you see kind of the inverse in M almost. So I was wondering, and they are degenerate with each other. So maybe that's part of the problem.
Well, maybe that. I'm not sure.
Yeah, it makes sense. So I think it would be interesting to, I think people are working already on joint Fourier space and configuration space constraints. And if this is the case, this bias should cancel out in some sense.
Yes, yes.
No one else has a question. I have like maybe a slightly follow-up question. So you had, so here in your left-hand side on the full shape, the AS looks kind of close to the peak, but you had another triangle protrude from the unit stems. And
Yes.
their AS constraints look oh, no, actually, no, actually, if I look at it again. Okay, so it's just again lower, but it's not that
Yeah.
not that dramatically slower. So okay. But there seems to be a tendency of AS being low as well, no? But yeah, it doesn't look dramatic.
Just well, yes, sure. For these two catalogs, these two simulations, just but as you say, it's not something problematic.
Rodrigo again?
Yeah, so can you go back to the constraints using neural network?
Sure.
Yeah, that one. So maybe I missed it, or I don't know. I don't understand exactly. So your N body is your training set for your neural network.
No. I'm generating hypercube using all the parameters that I want to vary in this model, and I'm using 20,000 multiples evaluated all around this hypercube, and I train the neural network using this 20,000 of multiples.
I see, but then you're just, this is just speeding up the calculation of the correlation function. Am I right?
Yeah.
So you still have to add on top your nonlinear corrections and the rest that you did before, right?
No, I am doing the full training for the
full nonlinear.
For the full model, yeah.
I see. Okay. I see. So is there a way to explain why you get much more accurate constraints? Because I would expect that if you're if you're just speeding up the calculation in the modeling is the same, why is the constraint better?
These are two different simulations.
Ah, I see, I see.
Yeah, these are data from the data release 12, and this is the NC MOOCs.
I see. Okay, makes sense. Okay, thank you.
I quickly just ask again, for this shape fit comparison between flops and your code, what's your S max, and how does it compare to the, or do you know the K-min of Holmes, and how they compare?
Using a K max much lower, you mean?
No, I mean, do you know what K-min Holmes
I
uses,
use
and what's your S max?
I don't remember the exact number, but we are using the same K min to get the linear power spectrum.
Okay.
But the exact number I don't remember.
Okay, yeah. And did you try that with other? So this is ELGs?
This is what?
This is for the ELGs, or?
Yeah, it's for the ELGs.
Did you try that for other traces as well, or?
Well, we are in that step. We are running some jobs to get this for other traces.
Does anyone else have a question? I'll ask one question maybe. So if, at the end you mentioned the Korobov distribution, could you briefly tell us what that is?
Yes, this Korobov distribution makes that all the points that we are using to train the neural network have a structure that allows the neural network to train in a better way. So they are distributed like in a well-sampled way, not randomly distributed, but they have a good structure in the parameter space, but at the same time they are well separated, and yeah, this allows to the neural network to get better training for the multipoles.
I see. Maybe we should read up on that.
Maybe upload help.
Yeah, maybe. Yeah. But I guess it's quite difficult to explain without and with them. Are there any other questions or no? Not where. Where do you go?
Yeah, so just one last question. Have you tried comparing this for extensions to Lambda CDM? So these two approaches?
No, we haven't done the. You mean something like the first plot that I showed, right?
I mean, just like varying W, let's say, or something. Not even modified gravity, just varying the equation of state of dark energy. I guess by opening up new degeneracies.
No, we haven't done that
Oh, I
yet.
see.
Okay. Well, the hour is up, so I guess we can close the official part here.